What if everything you think you know about what's inside a black hole is wrong? Consider this. We've been taught that a black hole is an end, a cosmic drain where matter falls in and simply ceases. But what if that's not the full picture? What if, buried beneath the mathematics we already have, general relativity, quantum mechanics, there's a radical possibility hiding in plain sight that the interior of a black hole isn't a death sentence for information, but a doorway to an entirely separate universe. Not science fiction, not speculation dressed up in pretty language. A genuine consequence of equations that have been tested, challenged, and survived. Welcome. If you're the kind of person who refuses to accept it just disappears as a satisfying answer, you're in exactly the right place. Today, we're going to think carefully, step by step, about why some of the most serious physicists alive believe that black holes may not destroy what falls into them, but contain entire new worlds. Stay with me until the end. This idea builds, and if you leave early, you'll miss the piece that makes the whole thing click. And if rigorous, honest, deeply interesting physics is what you're here for, hit subscribe. There's a lot more where this is coming from. Let's begin. Let's start at the beginning, not with black holes, but with something simpler. Escape velocity. If you throw a ball upward, it comes back down. Throw it harder, it goes higher before returning. But throw it hard enough, about 11 kilometers per second from Earth's surface, and it escapes entirely. It never comes back. That speed is called the escape velocity, and every massive object has one. Now here's the key question. What happens when escape velocity equals the speed of light? Because light is the fastest thing in the universe. Nothing, no signal, no particle, no information, travels faster. So if escape velocity reaches the speed of light, then nothing can escape. Not even light itself. That boundary, the surface where escape velocity equals the speed of light, is what we call the event horizon. And the object whose gravity creates that boundary is what we call a black hole. But here's where I want you to slow down and think carefully, because the popular picture is almost always wrong. The event horizon is not a wall. It's not a surface you could touch or feel. It has no substance. If you were falling freely toward a sufficiently large black hole, you would cross the event horizon without feeling anything unusual at all. No jolt, no signal, nothing. In fact, you wouldn't even know precisely when you crossed it. The event horizon is not a physical barrier, it's a geometric boundary, a point of no return written into the structure of space-time itself. This is where Einstein's general relativity becomes essential. In general relativity, gravity is not a force pulling things together the way Newton described it. Gravity is the curvature of space-time. Massive objects bend the fabric of space and time around them, and what we experience as gravitational pull is simply the natural path, the straightest possible path through that curved geometry. Near a black hole, space-time curves so severely that all straight paths, all possible futures, point inward. Think about that carefully. It's not that you lack the engine power to escape, it's that every direction forward in time leads deeper in. The geometry itself has been bent to the point where outward no longer exists as a viable direction. This was first made mathematically precise through what are called the Schwarzschild solutions, the first exact solutions to Einstein's field equations, worked out in 1916. Carl Schwarzschild found that surrounding any sufficiently compressed mass, there exists a critical radius, now called the Schwarzschild radius, at which the curvature of space-time becomes so extreme that escape becomes geometrically impossible. For the Sun, that radius would be about 3 kilometers, the Sun compressed to the size of a small city. For Earth, it's less than a centimeter. In nature, this compression happens when massive stars exhaust their fuel and collapse under their own gravity, unable to generate the outward pressure needed to resist it. And here is what I want you to hold on to as we move forward. The event horizon is a global feature of space-time, not a local one. You cannot detect it by what's happening around you in the moment. It is defined not by what you feel, but by what is possible from that point onward. That distinction between local experience and global geometry is going to matter enormously as we go deeper. Because what general relativity says happens beyond that horizon is where things get genuinely strange. And that's exactly where we're headed next. Now that we understand what the event horizon is, and more importantly, what it isn't, let's ask the next honest question. What does general relativity actually tell us happens inside a black hole? Not what movies suggest, not what pop science simplifies. What do Einstein's equations, taken seriously and followed carefully, actually predict? Let's begin with something that might surprise you. General relativity does not say the interior of a black hole is empty, featureless, or even particularly exotic, at least not immediately. For a sufficiently massive black hole, the region just inside the event horizon looks, locally, almost ordinary. The curvature of space-time there is actually quite mild. An astronaut falling through the horizon of a supermassive black hole, 1/1000 of times the mass of O. You, our sun, would notice nothing dramatic at the moment of crossing. The tidal forces, the stretching effects of gravity would be gentle, comfortable even. This is a deeply important point. The strangeness of a black hole is not concentrated at the horizon. The horizon is locally unremarkable. The strangeness is encoded in the global structure and where all paths lead from that point forward. So what do those paths look like inside? According to general relativity, once inside the event horizon, every possible trajectory, every future directed path through space-time leads toward the center, not because of some overwhelming force pulling you inward, but because the geometry of space-time inside the horizon is oriented that way. The radial direction toward the center becomes, in a precise mathematical sense, a time direction. Moving toward the center is not moving through space. It is moving through time. You cannot stop it any more than you can stop time itself from advancing. And at the center, or more precisely at the end point of all those inward-directed futures, general relativity predicts a singularity. A singularity is not a place. It's important to understand that. It is a boundary of space-time, a point where the curvature of the geometry becomes infinite, where the equations break down completely and cease to give meaningful answers. It is, in the most literal sense, the edge of what general relativity can describe. Now, physicists take this breakdown seriously. When a theory produces an infinity, that's not a result. That's a signal that the theory is being pushed beyond its domain of validity. General relativity is extraordinarily successful across an enormous range of scales, but it is not a quantum theory. And near a singularity where densities and curvatures become extreme beyond imagination, quantum effects cannot be ignored. Whatever actually happens there requires a theory we don't yet fully have, a complete theory of quantum gravity. But here is the remarkable thing. Between the event horizon and the singularity, general relativity is not silent. The equations have solutions, real mathematically consistent solutions that describe the geometry of space-time throughout the interior. And some of those solutions, particularly the solutions for idealized, non-rotating, eternal black holes, reveal something extraordinary. The full mathematical structure, when you extend the Schwarzschild geometry to its complete form, doesn't describe just one region of space-time. It describes two exterior regions, two separate spaces connected through the black hole's interior. This is not an assumption. It is not a speculation. It is what the mathematics produces when you take Einstein's equations seriously and extend them to their full, maximally complete solution. That mathematical structure has a name, and it has a diagram that makes it visible. And that's precisely where we're going next. So far, we've been working entirely within general relativity. And within that framework, the story is clean, consistent, and mathematically precise. But now we need to bring in the other great pillar of modern physics, quantum mechanics. And when we do, something goes seriously wrong. Not wrong in a minor technical sense, wrong in a way that strikes at the foundations of both theories simultaneously. Let's build this carefully. Quantum mechanics rests on several deep principles, but one of them is absolutely non-negotiable. It is called unitarity. And what it says in plain language is this: information is never destroyed. Now, when physicists say information, they mean something precise. They mean the complete specification of a physical state, the exact arrangement of all particles, all fields, all quantum nu. members that describe a system. Quantum mechanics says that this information, while it can be scrambled, encoded, redistributed, hidden in enormously complex ways, can never be permanently erased. The laws of physics at the quantum level are reversible. Given the final state of a system, you could, in principle, reconstruct every detail of its past. This isn't a philosophical preference, it is a mathematical requirement baked into the structure of quantum theory. Violate unitarity, and the entire framework collapses. Probabilities no longer add up to 1. Predictions become meaningless. Now hold that principle firmly in mind, and let's return to black holes. In 1974, Stephen Hawking made a stunning discovery. When you apply quantum field theory, the marriage of quantum mechanics and special relativity, to the region just outside a black hole's event horizon, you find that the black hole is not entirely black. It radiates. Slowly, quietly, but genuinely. It emits what we now call Hawking radiation. The mechanism is subtle. Near the horizon, quantum fluctuations constantly produce pairs of particles, one with positive energy, one with negative energy. In ordinary space, these pairs annihilate almost immediately, but near the horizon, one particle can fall inward while the other escapes outward. The escaping particle carries energy away from the black hole. Over enormous timescales, this process causes the black hole to lose mass, slowly, steadily, until it evaporates completely. And here is the crisis. Hawking showed that this radiation is, to an excellent approximation, thermal. Random, it carries no detailed imprint of whatever fell into the black hole. A black hole formed from collapsed hydrogen and a black hole formed from collapsed encyclopedias would, according to Hawking's calculation, produce identical radiation, which means that when the black hole fini, Ly evaporates, when it is completely gone, all the information that ever fell into it appears to be gone too. Not hidden, not scrambled, destroyed. This is the information paradox, and it is not a small puzzle. It forces a direct contradiction between two of the most successful theories in the history of physics. General relativity says information falls in and is lost. Quantum mechanics says information cannot be lost. Both cannot be right. Physicists have spent decades on this problem. Susskind himself devoted years and a famous scientific argument with Hawking to resolving it. His conclusion, and now the broad consensus, is that information must escape, that Hawking's original calculation, while brilliant, was incomplete, that quantum gravity effects, subtle and non-local, must encode the information in the outgoing radiation in ways we do not yet fully understand. But resolving the paradox may require us to completely rethink the interior of the black hole. And that rethinking leads us directly to the most powerful geometric tool we have, a diagram that maps all of space-time at once and shows us something remarkable hiding in the structure of the mathematics. That's exactly where we turn next. We've arrived at one of the most powerful and beautiful tools in all of theoretical physics. And like the best tools, it looks deceptively simple at first glance. It's called a Penrose diagram, named after the mathematician and physicist Roger Penrose, who developed it as a way to represent the entire structure of space-time. All of it, past and future, near and infinitely far, compressed into a single finite picture you can hold in your mind at once. Let me explain how it works, because understanding the diagram is understanding the physics. In ordinary space-time diagrams, we plot space on one axis and time on the other. A point on the diagram represents an event, a specific location at a specific moment. A line represents a trajectory through space-time. And the fundamental rule of relativity is that nothing travels faster than light, so light rays always travel at 45 degrees on these diagrams, forming what we call the light cone around every event. Now, Penrose's insight was this. You can mathematically compress infinite space-time, all of it, stretching forever in every direction, into a finite diagram while carefully preserving those 45-degree light cone angles. The compression distorts distances and durations, but it preserves the causal structure. It preserves what can influence what. And that causal structure is precisely what matters most in general relativity. When you draw the Penrose diagram for flat, empty space-time, you get a square tilted 45 degrees, a diamond. The entire infinite universe, past and future, fits inside that diamond. Light rays still travel at 45 degrees. Massive objects travel on paths steeper than 45 degrees, always confined within their light cones. Now draw the Penrose diagram for a black hole. Specifically, let's consider the idealized case, a perfectly symmetric, non-rotating, eternal black hole. The full mathematical solution to Einstein's equations in this case is called the Kruskal-Shaker's extension of the Schwartz geometry. And when you draw its Penrose diagram, something immediately striking appears. The diagram divides into 4 distinct regions. The upper region is the black hole interior, the region beyond the event horizon from which nothing can escape, where all futures lead to the singularity drawn as a jagged line at the top. The lower region is something called a white hole, a time-reversed black hole, a region from which everything escapes and into which nothing can fall. It's the exact temporal mirror of the black hole. General relativity permits it mathematically, though we have no observational evidence that white holes exist in nature. The right region is our universe, the familiar exterior space-time from which we observe the black hole. And then there is the left region, a complete separate exterior space-time, mathematically identical to ours. Another universe, if you will, connected to ours only through the black hole's interior, but causally disconnected. No signal, no particle, no information can travel between the right and left regions. They share the interior geometry, but they cannot communicate. This connected structure has a name, an Einstein-Rosen bridge. You may know it by its more popular name, a wormhole. But here, in the Penrose diagram, you can see exactly what it is and exactly what it means. Not a tunnel you can travel through, a geometric connection between 2 regions of space-time that are causally sealed from one another. Now, this is the eternal, idealized black hole. Real black holes form from collapsing stars, and their Penrose diagrams look somewhat different. The left region and the white hole don't appear in the same way. But the mathematics of the eternal solution is not mere abstraction. It represents a genuine feature of what general relativity permits. And in recent decades, ideas from quantum gravity, particularly from string theory and holography, suggest that something like this connected structure may be deeply real and deeply connected to the information paradox we discussed earlier. The Penrose diagram doesn't just organize our knowledge. It reveals structure that was always hidden inside the equations, waiting to be seen. And what that structure ultimately suggests about the nature of what lies beyond the horizon, that's the question we take on next. We've come a long way. We started with escape velocity and the geometry of the event horizon. We followed Einstein's equations into the interior. We confronted the information paradox, the deep conflict between general relativity and quantum mechanics. And we saw in the Penrose diagram that the mathematics of an eternal black hole describes not one universe but 2, connected by an Einstein-Rosen bridge. Now let's ask the hardest question of all. What does this actually mean? Is the other region real? And if so, what is it? Let's be precise about what we're claiming and what we're not. The eternal black hole solution, the maximally extended Schwarzschild geometry, is mathematically exact. It is a legitimate solution to Einstein's field equations. The 2 exterior regions it describes are both geometrically valid. In that strict mathematical sense, general relativity does not merely permit another universe connected to ours through a black hole. It produces one automatically when you take the equations to their logical completion. But mathematics permitting something and nature realizing it are different questions. And this is where we need to think carefully. Real black holes in our universe are not eternal. They form from the gravitational collapse of massive stars. They have a beginning. And the Penrose diagram for a collapsing black hole, as opposed to an eternal one, does not contain the second exterior region in the same way. The wormhole, in the realistic case, does not connect to a fully developed separate universe that existed before the black hole formed. So does that close the door? Not entirely. And here is why. In the 1990s, physicists studying quantum gravity, particularly in the context of string theory and what's called the holographic principle, began finding something unexpected. When you analyze the quantum states of a black hole with extreme care, the mathematical structure that keeps appearing is not that of a single isolated system. It has the character of two angled systems, two sets of degrees of freedom deeply correlated with one another, even when they cannot directly communicate. This is precisely the structure of the eternal black hole's Penrose diagram, two exterior regions quantum mechanically entangled through the interior. Juan Maldacena, building on this, proposed something profound, that the Einstein-Rosen bridge, the wormhole, and quantum entanglement may be at the deepest level the same phenomenon. That geometric connection through a black hole interior is the gravitational manifestation of quantum entanglement between two systems. This idea is sometimes summarized as ER equals EPR, Einstein-Rosen bridges equal Einstein-Podolsky-Rosen entanglement. A striking, still debated but deeply serious proposal. And then there is the idea of baby universes, a related but distinct concept. In certain quantum cosmological models, the interior of a black hole, rather than terminating at a singularity, undergoes a process analogous to inflation. A new region of spacetime buds off, expands, and becomes causally disconnected from the original universe. Not a pre-existing parallel universe, but a new one born from the interior geometry of a collapsing black hole. This is speculative, let's be honest about that. We do not have a complete theory of quantum gravity. We cannot yet observe the interiors of black holes. These ideas live at the frontier, supported by mathematical consistency and deep theoretical hints, but not yet confirmed by experiment. And yet, and this is what I want you to take away, these are not the idle speculations of science fiction. They are the serious, mathematically grounded consequences of following our best physical theories to their limits. General relativity points toward connected geometries. Quantum mechanics points toward entangled structures that mirror those geometries. The overlap bet, wean, those two arrows is where the deepest physics lives. We began this video with a question, might black holes contain another universe? The answer general relativity and quantum gravity give us is neither a confident yes nor a dismissive no. It is something more intellectually honest and more exciting than either. It is. The mathematics strongly suggests it, the physics demands we take it seriously, and we do not yet have the full theory needed to settle it. That unresolved frontier is not a failure of physics. It is an invitation, the invitation to build a theory that will finally tell us what space-time and information truly are, beyond every horizon we have yet crossed. Thank you for thinking this through carefully. This is exactly the kind of question that drives physics forward. Let's take a moment to retrace the ground we've covered, not to repeat ourselves, but to see the full shape of the argument, now that we've built it piece by piece. We started with something familiar, escape velocity, and followed it carefully to its logical extreme, a region of space-time where the curvature becomes so severe that every possible future points inward. That's the event horizon, not a wall, not a dramatic boundary, a geometric point of no return, invisible to someone crossing it, but absolute in its consequences. We then asked what general relativity actually says about the interior, and found that the equations don't go silent beyond the horizon. They continue. They produce solutions. And when you extend those solutions to their complete mathematically honest form, they describe not one region of space-time, but two. Two exteriors connected to the interior geometry of an eternal black hole, an Einstein-Rosen bridge, a wormhole not as a science fiction device, but as a direct consequence of Einstein's field equations taken seriously. Then we brought in mechanics and found a crisis. Hawking radiation suggests that black holes evaporate and that the information describing everything that ever fell in appears to be destroyed in the process. But quantum mechanics says information cannot be destroyed These two conclusions cannot both be true. That tension, the information paradox, is not a footnote. It is one of the deepest unsolved problems in theoretical physics, and resolving it may require us to fundamentally revise how we think about space, time, and the interior of black holes. The Penrose diagram gave us the geometric language to see all of this at once, to hold the entire causal structure of space-time in a single picture and recognize what the mathematics was quietly telling us all along. And finally, we arrived at the frontier. Baby universes, quantum entanglement as geometry. The ER equals EPR conjecture. Ideas that are speculative, yes, but speculative in the way that serious theoretical physics is speculative, grounded in mathematics, constrained by consistency, and pointing toward a deeper theory we are still in the process of building. So, do black holes contain another universe? The careful answer is this. General relativity says the complete geometry of an eternal black hole includes a second exterior region. Quantum gravity suggests that entanglement and geometry may be two descriptions of the same underlying reality. And the full theory that would settle the question definitively, a complete consistent theory of quantum gravity, remains one of the great open problems of our time. That is not a frustrating answer. That is an honest one. And in physics, honest answers at the edge of knowledge are the most valuable kind. They tell you exactly where to push next. If you followed this argument all the way through, if you sat with the geometry, took the paradox seriously, and let the mathematics see as speak, then you've done something genuinely worthwhile. You've thought carefully about one of the deepest questions in modern physics. Not just what the answer might be, but why physicists ask the question at all, and what the current state of understanding actually looks like. That's what rigorous physics feels like. Not a collection of surprising facts, but a coherent web of reasoning that you can follow, test, and build on. If that's the kind of understanding you're here for, subscribe. Every video on this channel is built the same way, from the ground up, step by step, with no shortcuts and no hand-waving, just careful thinking about ideas that genuinely matter. There's a great deal more to explore, and the next question is already waiting. Thank you, genuinely, for sticking with this all the way through. These aren't easy ideas. The geometry of space-time, the information paradox, the mathematical structure hiding inside a black hole, this is material that professional physicists spent decades wrestling with. The fact that you chose to sit down, follow the reasoning carefully, and think it through seriously, that means something. Physics at this level isn't about memorizing answers. It's about learning to ask better questions. And if you leave this video with a clearer sense of why these questions matter, not just what the current best guesses are, but why the problem is deep, why it resists easy answers, why the smartest people in the field are still working on it, then we did something worthwhile together today. That's really what this is all about. Not impressing anyone with complicated terminology, just a quiet satisfaction of understanding something a little more honestly than you did before. That feeling never gets old. At least, it never has for me. So thank you for your time, your attention, and your willingness to think carefully. It's a rare thing, and it's genuinely appreciated. Take care of yourselves, and I'll see you in the next one.